Hello everybody, my name is Danielle Weigel, and today we are going to be completing the third and portion A, and the next video will cover portion B. As you can see, the goals for today are going to be explaining the Lewis relation and then how it's used as a part of the energy balance to determine the relative humidity from wet and dry bulb temperatures, and then explain the relationship between the adiabatic saturation temperature and the wet bulb temperature. So let's get started with the first portion, which is explaining the Lewis relation. And the first thing that we want to look at is, what is the Lewis relation supposed to do? The Lewis relation defines a relationship between the mass transfer coefficient and the heat transfer coefficient. And it involves the Lewis number, which is defined as the thermal conductivity over the thermal diffusivity over the mass diffusivity constant. And so the first thing that we're going to look at are equations that we already know relating to mass transfer and heat transfer. So we'll look at mass transfer first. In mass transfer, we have our convective, heat transfer. We have our convective heat transfer, and we have conductive heat transfer. And in our convective heat transfer equation, we know that the heat transfer is equal to the heat transfer coefficient times the difference in temperature at the surface and the temperature at the environment. And in our conductive heat transfer, we know that it is equal to the negative of the conductivity of the material, and that is times the change in temperature over the change in distance. And then we are going to look at our mass transfer equations. And the first one that we have is our flux, our molar flux equation. Which is equal to the mass transfer coefficient, Kc, times the change in concentration at the surface and the concentration of the environment. And then we have our molar diffusive flux, which is equal to the opposite of the diffusivity coefficient times the change in concentration per the change in distance. And what you're going to notice right away is that these sets of equations are set up very similarly, with temperature being replaced by concentration and then just the different variables. And so the next thing that we're going to do is look at a couple of these dimensionless groups that we were discussing in the previous exam, dealing with heat transfer and mass transfer. The first one that we're going to look at is the Sherwood number, and the one that we're going to look at is the Nusselt number. The Sherwood number is equal to the mass transfer coefficient times the distance or diameter over the diffusivity constant, and then we also have the Nusselt number, which is equal to the heat transfer coefficient over the distance, or the distance over the conductivity. And then we also define these with further dimensionless variables with the relationship of A times the Reynolds number to some power B times the Schmidt number to some power C. And the Nusselt number was defined as A times the Reynolds number to some power B times the Prandtl number to some power C. And so right away, when we look at just the relationship between these two numbers, we get that the Sherwood number over the Nusselt number is equal to Kc times the mass transfer coefficient times the distance over the mass diffusivity constant, and then times the conductivity over the mass transfer heat transfer coefficient times the distance or diameter. And we see that those cancel out, and we would get the mass transfer coefficient times the material's conductivity over the mass diffusivity constant times the heat transfer coefficient. And then we can look at this second portion of the equation and see that this section, since these variables a, b, and c are all the same, this would cancel out and leave us with the Schmidt number over the Prandtl number to some power c. So then we can further redefine the Schmidt number and the Prandtl number into their definitions. And the Schmidt number is the viscosity over the density times the mass diffusivity constant, and the Prandtl number is the viscosity over the density times the thermal diffusivity. And so when we look at this Schmidt over Prandtl number, we would end up with the these canceling out, and it would be equal to the thermal diffusivity over the mass diffusivity. Which, when we look at that, we can see that that is actually the Lewis number. And so we can also say that the Sherwood number over the Nusselt number is equal to the thermal diffusivity over the mass diffusivity to some power c, which is also equal to the Lewis number to some power c. And that gives us our Lewis relation, the summary between these. We can say that the Lewis number to some power c is equal to the Sherwood number over the Nusselt number, which is also equal to the mass transfer coefficient times the material conductivity over the mass diffusivity constant times the heat transfer coefficient. And that is our Lewis relation. And so then by getting more information on either the mass transfer or the heat transfer, we can determine information about the other one, the heat or the mass transfer. And that's what we are going to be doing in part 2 of section A. So now we want to determine how to use the Lewis relation as part of the energy balance to determine relative humidity from wet and dry bulb temperatures. The concept of using wet and dry bulb temperatures to determine relative humidity comes from the idea that if you have a thermometer wrapped in something wet and then you swing it around, liquid will begin evaporating from the surface of the thermometer bulb, and it will give you a lower temperature reading since energy is needed to convert that liquid water to a gas. That's taken from the temperature, so that will give you a lower temperature reading, and the dry thermometer will give you the actual ambient temperature of the environment, and you can use that comparison to determine your relative humidity. The equation for relative humidity is the partial pressure of water at the surface over the saturation temperature, or the saturation partial pressure of water at some given value of temperature. This number can be determined through an Antoine's equation. So what we need to do is determine this value right here. The first thing that we're going to do is we know that our relation is, we know that our Lewis number can be defined as the thermal diffusivity over the mass diffusivity, and we're going to further bring that down into terms of the thermal diffusivity, which is equal to the conductivity over the density times the heat capacity, which is actually the volumetric heat capacity, so that's what I will be calling that term. So when we look at this Lewis relation and how it relates to this part of the equation up here, we can see that we're going to be able to make some connections. First of all, let's look at what the Lewis number would be for like moist air. When we rewrite this Lewis equation, we get that the Lewis number is equal to the conductivity over the mass diffusivity times the volumetric heat capacity. And these are all known values for moist air. And what you're going to find is that when you plug this in for moist air, the Lewis number is actually equal to 1. And that allows us to do a couple of things, rearrangement of equations that allow us to set things equal to each other, which is really helpful in the temperature, or in the scheme of moist air. So since we know that the Lewis number is equal to 1, we can rewrite, we can set the conductivity over the mass diffusivity equal to the volumetric heat capacity, and then use that relationship in this equation up here to replace our these two numbers. So we have our mass transfer coefficient over our heat transfer coefficient times the volumetric heat capacity, and we can set that equal to the Lewis number to the c power. But any number, any time 1 is set to any power, it's going to be equal to 1. So we know that this is also equal to 1, which we can then allow us to say that the mass transfer coefficient over the heat transfer coefficient is equal to the specific volumetric heat capacity. That is the first thing that we need to determine and prove. And then we can look at our energy balance for the mass and heat transfer. Our heat transfer equation that we mentioned earlier is going to be the heat transfer coefficient times the difference in temperatures. In this case, the temperature of the environment is higher than the temperature at the surface of the bulb, so we are going to write them in this order. And then that we also need to include the mass transfer, which is the mass transfer coefficient times the difference in the concentration at the surface minus the concentration of in the environment, because that's going to be lower than the surface. So but we want to find an actual way to relate these, and when you look at the units involved in this, we have meters per second and moles per meter cubed, and here we have watts per meter Kelvin and Kelvin. This is also equal to joules per meter second Kelvin. And we can then cancel these out. And so this side of the equation has joules per meters seconds. And this side of the equation has, or meters squared, sorry, this is joules per meter squared, watts per meter squared. And this side of the equation we get moles per meter squared seconds. And those obviously aren't equal to each other, but what we can include in this equation is the heat of vaporization. The heat of vaporization has the units of joules per mole. And so that will have our moles cancel out and give us joules per meter squared seconds. So this is our equation, our energy balance equation relating those two together. And what we have to do next is then write this in terms of our ideal gas law equations. What we can replace are these concentrations and another factor that we will introduce right now, because we don't know these two values. But what we did up here is we found this relationship that we can use to put them in terms of known values. So when we rewrite this equation so that we can actually use this, we have the heat transfer coefficient over the mass transfer coefficient times the difference in our temperatures is equal to the heat of vaporization times the difference in the concentrations. We use this relationship to replace these with our known values, our volumetric heat capacity, to give us this equation. And as I mentioned before, these are the two values that we can replace using our ideal gas law, but we can also replace the density. And so our density would be equal to the total pressure over the temperature, the average temperature times the gas constant, and then the concentration at the surface is equal to the pressure at the partial pressure of water at the surface times the temperature at the surface times the gas constant, and the concentration of the environment is equal to the partial pressure of water in the environment over the temperature of the environment times the gas constant. And when we looked at our units earlier, we know that the temperature has to be in terms of Kelvin, and the differences in temperature is going to be relatively small, only a few degrees Kelvin. So we can actually go ahead and assume that these values are equal to one another, or approximately equal to one another, which will allow us to cancel out these bottom parts of the units, which will give us our kind of final relationship equation as the total pressure times the heat capacity times the difference in temperatures times the heat of which is equal to the heat of vaporization times the difference in the pressure at the surface minus the partial pressure of water in the environment. And we can go ahead and isolate this value that we can then plug in up here for our relative humidity. Alrighty, so in part 3 of this exam, what we want to do is show the relationship between the equations that you would get, these energy balance equations that you would get in the situation of an adiabatic saturation temperature and the wet bulb temperature. So in order to illustrate what the adiabatic saturation temperature situation would look like is that we have this infinitely long tube, and in the tube we have water flowing and air flowing. So we have some mass flow rate of air going in and out. We have the initial temperature of the air going in, and the initial pressure of the water in the air, the partial pressure of the water in the air going in and out. And then we also have the temperature of the water flowing along the bottom. Since this tube is infinitely long, we can assume that the partial pressure of the water going out would be equal to the partial pressure of the water, or the partial pressure of the saturation, the partial pressure of the system when it is fully saturated at the temperature of the water. So that can end up being a known value. This is a steady state system. So when we are creating our energy balance, we want to find the enthalpy in and set it equal to the enthalpy out. So in order to begin this equation, what we're first going to look at is we have this mass flow rate of air in kilograms per second. we need to include our heat of vaporization, which is in joules per kilogram. And then we need to include our difference in concentrations, but in terms of partial pressures, since our goal is to create an equation that looks similar to this. Our initial concentration going in, we have the partial pressure of the water going in over the gas constant times the temperature. But since we are using the mass of air here and the partial pressure of the water vapor here, what we need to do is also include the specific volume of the water vapor in the air, and that we can do by using the total pressure over RT. And what we need to include here is that we notice that this would be in terms of moles, and what we need are kilograms. So we also need to include the molecular weight of water here and the molecular weight of the air, the average molecular weight of the air here, in order to keep these kilogram terms in matching with these terms. So we have this situation, and then we also need to include our heat capacity. So we have that, and the difference in our temperatures. So for enthalpy going in, we have the temperature of the air going in, minus some reference temperature, which we are going to set at 0 for ease, so that can cancel out. And that gives us the enthalpy in. And so for enthalpy out, we are going to be using the same type of situation. We have the mass flow rate of air, the heat of vaporization, this time with the partial pressure of the water vapor going out, with the molecular weight of water over RT, and the specific volume as well. And then the addition of the heat capacity term with T, with the temperature of air going out. And once again, the reference temperature is still 0, so we don't have to include that. So immediately looking at this equation, there are some things we can cancel out. We can cancel out this mass flow rate of air, and then we can look at the equation as something being set to 0. For ease of not rewriting it and time saving, I'm just going to write it like this. And then we can go ahead and begin combining terms for this term and this term and this term and this term. We'll start with the heat capacity because that one's simple. We have the heat capacity times the difference in the temperature of air going in and the temperature going out. And then we have this term including the heat of vaporization, which has our, we can remove these, cancel out, and then these are common terms between the two of them. So we can pull that out as well. And then that gives us the difference in the partial pressure going in. And as we discussed up here, the partial pressure of water vapor in the system at the saturation. that is equal to 0, but that means that we can also just set them equal to each other. Once again, just for ease of not rewriting it. But we are going to end up rewriting it because we want this to really look at, to be comparable to our wet bulb temperature up here. So we can move our P total over here and our molecular weight average over here. I'm just going to rewrite it over here. We have P total times the average molecular weight times the differences in temperature and that is equal to the heat of vaporization times the molecular weight of the water vapor times the difference in the pressures going in and out. I did forget to carry over my negative sign here. Yes. So we can swap the order of these. So then when we look at our comparison up here for the wet bulb, and here's our energy equation for the adiabatic system, we can see that the only difference is this molecular weight average that has been inserted into the equation. And this is because we were originally looking at the heat of vaporization in terms of joule per kilogram here, but when we were looking at it here, we had it in terms of joules per mole. So if we had used the joules per kilogram in our initial wet bulb equation, we would have also had to include the molecular weight of water and the average molecular weight. In these equations. So you can see that they are actually identical. And so that covers section A of exam 3. In the next video, we will cover section B.